Okay, so I am sharing the screen, and if anyone has any comment from the past, from the last session at all. So we covered spectroscopy, and prior to that we covered imaging. And then we're gonna introduce new topic today, thickness profiling. So the question is, what's the big deal about thickness profiling, etc.? And let's go through this a little bit here and see if we can make some sense. So I'll go to the presentation mode. So first example of thickness profiling, the purpose of thickness profiling will be clear as we go through it. But this is a technique for monitoring or tracking permeation of some analyte into some substrate in real time. And that has application in transdermal drug delivery, characterization of any membrane, and we have applied it to skin as well, and few others as we'll go through. So first example is skin. As you know, skin is the biggest organ of our body, and it has the skin cancer particularly is on the rise. So this technique or technology has implication or has application for very early detection of skin cancer. We have demonstrated that by imaging. We saw in imaging that on the onset of tumor formation, skin cells agglomerate, which is quite different than the healthy skin. And then based on that image, we can determine and locate the cancer position. And doctors can then use it as a diagnostic tool. Other part of the same approach is that the skin is a layered structure. So this layering definition also changes as the cells agglomerate on the onset of tumor formation. The layering structure changes as well. And we can monitor that by thickness profiling, by T-ray, because T-ray is penetrating through the skin. So this can be applied to both excised tissue, ex vivo, as well as in vivo, because this is non-ionizing radiation, so it does not cause any radiation dose or damage. So it is useful for live patient diagnosis as well. Calibration of the sample holder. So first of all, the experimental arrangement is there. I think here we go. This is the experimental arrangement. So if this is skin or a substrate, then when we put some analyte or solution on it, that will permeate into that substrate. And then we can measure that permeation in real time. And so this should have been at the beginning, but we'll come back here. So what happens is, if we do a depth scan of the empty cell, there's not much going on. It's pretty monotonous. Now, we put in this case, what we have done is um, of a benign skin. That skin has no cancer in it. And then thickness profile from scan of a benign skin or healthy skin, you want to call it that way. The skin thickness profile is obtained by subtracting the reference. So first we have the reflected intensity of the sample holder run, and then subtract that from the scan of the skin itself. That gives us the profile. And as you can see, the red curve shows a lot of layering of that spot where the skin was taken from. And then if we compare that with a cancerous skin, which is the sample number is not very clearly identified here, but the sample 1448A minus the reference, that shows that wherever we had in the healthy skin, the layering what happened. In the skin with cancer, that layering definition has either gone or subsided significantly. So, and this scanning doesn't take very long. This is almost few-second scan. So it's applicable for diagnosis. That tells us that something is wrong here. And then, of course, we do the imaging and we do the spectroscopy as well to compare everything with respect to a healthy or benign skin sample. And that allows us the tool for diagnosis. But here, what we are doing is we are going to measure the permeation of analytes into the skin in real time. That's the goal of this point. So measurement of concentration gradient in a non-invasive or non-destructive way is important for transdermal drug delivery. So how we do that? First, we utilize the laws of diffusion. So Fick's first law is the flux. Flux is simply the available molecules per unit area. And that, constant diffusion under gradient is the concentration is dependent on the thickness or depth. So d dx is the, dc, c is the concentration, d is the diffusion coefficient, and so d dx is the gradient of distribution across the thickness. So the complete characterization of the diffusion requires two things. First, the gradient, and second, the kinetics. So dc dt, which is the time-dependent change in the concentration, and dc dx, which is the thickness-dependent change in the concentration of a molecule that is permeating into something. So it's always a substrate and solute combination. So dc dt in, let's say, in a piece of paper will be one thing, but dc dt of the same solute in a different substrate will be different. So that's the dc dt, dc dx. And so is the kinetics. The rate of permeation will also be different. So once we know this rate of permeation and the distribution of molecules within the substrate, then we can measure the D. It's a complete characterization of diffusion process. by the Fick's first law and second law. And how do we apply that here? That is the question. So to quantify the bioavailability of nanoparticles in this particular example, and then they quantify the kinetics and concentration gradient of actives in this case, the substrate is the stratum corneum. So stratum corneum is the very top portion of the skin. So that is the barrier. If an analyte goes through the stratum corneum, that means overcomes the barrier, then it can go into the bloodstream. That's the philosophy for the transdermal drug delivery. So again, this is the experimental setup. We measure the dCdt as well as dCdx. dCdx is a little difficult to measure, but dCdt is the, the kinetics is the first order of measurement. So here, as you can see, I have a piece of paper on which I have a drop of DI water. And as this water penetrates into the depth of that paper, the reflected intensity changes. So C0, which is concentration at the 0th time, is not changing. There's the reflected intensity corresponding to the reflected intensity of the blank paper or substrate, whatever the substrate may be. At this point, we have dropped that little drop of water, about 50 to 100 microliter. You use the micropipette to drop that kind of volume. And then the molecules of the water starts penetrating. As it starts penetrating, the reflected intensity is decreasing. And eventually it saturates because no more is penetrating in there. So this is the kinetics.
Question. Are you doing it in a cell, or how are you doing it in terms of collecting the response? This reflectance.
So this is basically this is the instrumental setup.
Mm-hmm.
We have an instrument, what we call is this vertical scanner or substrate scanner.
Uh-huh.
That on over here there is a sample holder or cell.
Right.
So we put the substrate on it,
mm-hmm.
and then at a given time, we put the solution on it. So what happens when you put the substrate and start tracking down, nothing is going on.
Uh-huh.
But as we apply the solvent or solution on it, it permeates, and this gives us the dCdt. So this is a direct measurement of dCdt.
Yeah, understood. But where is the glossy paper coming into the picture in terms of removing?
It's just an example to show how dCdt is measured.
Okay.
All right.
Okay.
Another point. Okay. So now that we see we can measure the kinetics permeation, then next stop to measure the concentration gradient. How we do that? It's a two-step process. So first we do the depth scan of the substrate alone. Then we do the kinetics experiment and allow it until saturation. And we wait until saturation. At saturation, now we know permeation has been completed. And then we do the depth scan again. And so the depth scan before and depth scan after gives us the concentration gradient across the thickness of that substrate. And again, that substrate can be, just about anything, including human skin. So we have a couple of examples of those kind of permeation First one is polyethylene glycol. The second one is the caffeine. Both of these experiments were done on human stratum cornea, not the whole skin, but the very top portion of the skin, stratum cornea. Those samples we received by collaboration from Rutgers University, and they received it from the Skin Bank in New York. So again, this is the actual cell, close-up of the cell, not the whole cell. And this purplish kind of color is the stratum corneum that is mounted on the cell. Mounting the stratum corneum on the cell takes a little while to get used to. Stratum corneum is very fragile structure. It can get ripped off very easily, especially when we keep it frozen. It remains in dry ice until we receive it, and then we start doing the measurement as soon as we can. But nonetheless, it is very fragile structure. So mounting it on the cell takes a little while. And then once we do that, what we have done here is the red curve is the propylene glycol. And the blue curve is 1% hydrocortisone in propylene glycol. So meaning that we are trying to quantify the permeation of hydrocortisone, which is a molecule dissolved in propylene glycol. Because those are the kind of formulation they use in practical topical solutions and stuffs like that. So what we have, once the saturation, so we first did scan the substrate across the thickness, then this kinetics experiment was done for both of them one at a time.
Can I ask a question?
Yes, please.
Can you go back? So what are those peaks or for the initial spikes for both cases?
Yeah, very important point. Well, thank you. Thank you for asking. Okay, so what happens is, this is where zero time, nothing is going on. So as soon as this solution is applied, remember the beam is under the surface, right? It's coming up, going back from the surface into the detector. So some of the beams are actually escaping through the stratum cornea. And we are not being able to account for that here. But as soon as we put a drop on it, then the beam that was escaping, many of that are not being able to escape. Therefore, this spike happens. So the actual kinetic starts here and goes all the way there. But in case of propylene glycol, there are a lot of jaggedness because the beam, reflected beam, did not, the substrate did not get saturated, or some kind of kinetic things going on there, interaction of the propylene glycol with the stratum cornea, which is the, all the spikes that is coming in the red curve. But when we have hydrocortisone in there, there is no jaggedness. In other words, the stratum corneum is now saturated with the propylene glycol. So either it's some nooks and crannies where all these things are happening, or some other kind of interaction going on that we don't know for sure. But the peaks are happening because some of the radiation that was escaping is not escaping. So the count goes up. And this, this kind of the ups and downs are happening because of something going on over that period of time with the stratum corneum and the solution that is dropped over there.
Is it repeatable for the
Absolutely.
propylene
Very, very
glycol?
repeatable. Yeah. Yes, very repeatable.
Okay. For the initial spike, multiple peaks, repeatable. All right.
It will, yeah, it is repeatable, but it will also depend on the solution, the analyte in it, as well as the substrate. So
Yeah,
the substrate will have its characteristic, this kind of thing.
Mm-hmm.
It also depends on, there are a few things here, also depends on the, so if you can imagine that I have a, I have to draw, the beam is coming from underneath, and I have to drop right on top of the beam. Sometimes it's not obvious because I'm not seeing the beam where the spot is because it is below the substrate. So if I don't put exactly on top of the beam, then kinetics will change a little bit. But the basic nature of the kinetics will not change.
Understood.
Yeah.
But follow-up question for propylene glycol alone, after a little bit of time, say 50 seconds or so, or maybe 30 seconds after the drop is injected, why it's going up?
It's going up because it is drying.
It's drying.
Yeah. So that's another thing also can be tracked with this technique, that if an analyte is staying within the substrate or is it drying? When it is drying, how fast it is drying, all of those things are important here.
Okay.
Okay, so again, this is remember the principle that I described here. We do the depth scan before, then we do the kinetics, and then we do the depth scan again, and subtracting them gives us the distribution of the analyte within the substrate. So here what has happened is this blue curve is the hydrocortisone in stratum corneum. Red one is the blank stratum corneum. So in other words, this blank stratum corneum was scanned first, which is this red curve. Then we did the kinetics experiment as I shown before with the 1% solution of stratum hydrocortisone in propylene glycol. And then after the kinetics saturated, we did the depth scan again. And if we take the difference of this red and blue curve, then we get the distribution of the hydrocortisone within the stratum corneum. So apparently, this is thickness. So stratum, the hydrocortisone is actually penetrating a little bit inside the stratum corneum. As you can see at zero time on the surface, which is the thickness equal to 0, and this is the green curve, green axis. So the count is less than at the depth of 30 micron, count is more. So now from this count, we can actually calibrate it in terms of the concentration of these molecules, which has not been done yet here. So these are, data were published in drug delivery and drug development and delivery. And we thank Professor Mishniak for helping us with this experiment, with the samples, etc.
So these counts, can you go back for a second? These counts are directly proportional to the concentration.
Exactly.
And you added 1%?
Yeah, 1% hydrocortisone and propylene glycol. Yeah.
So does it match with 1% concentration to the counts, or I'm sure you have standardized it or calibrated it?
No, we have not calibrated it. I'm saying that from this count, we can calibrate it in terms of the concentration. So what we have to do is make some non-concentration dependent measurement, several of them. If we can do that, that will allow us to calibrate, in terms of the concentration. Some other places that has been done, but not this one.
Okay.
No points?
No, that's good.
Okay, wonderful. So, and this this is another experiment of permeation kinetics of caffeine through stratum corneum. So we have seen that hydrocortisone actually penetrates through the stratum cornea. Otherwise, the count would not have been higher at the 30 micron depth. But what we have seen, the same experiment, that the caffeine does not penetrate. Caffeine has higher concentration on the surface, thickness equal to 0, but at thickness equal to 30 micron, it has a lot less count than on the surface. So maybe a little bit penetrated, but most of them they remain in the surface area. So caffeine do not permeate through stratum corneum, which is what we want. If it did permeate, then it would have been difficult. So we want the medication to go through. It's actually a very important subject of transdermal drug delivery. The barrier, they can enhance the permeation by some formulation, and they can also reduce the permeation, like in the when you want to put some lotion for stopping mosquito, and those are the kind of formulation that stops penetration, that strengthens the barrier. And the other one, there are other formulations that compromises the barrier of the skin for easier drug delivery. Okay, so this is a very useful experiment. As you can see, it's very simple, but it can be utilized for so many different things. Here is that this is the calibration Dr. Mazumdar was mentioning a little while ago. So we have DI water and we have glycolic acid. Again, glycolic acid is used. A lot of it are used in personal care products. So this was actually a project with one of the personal care product company. They were interested in it. So they provided us this glycolic acid solution at different concentrations. And when we did the permeation through the stratum corneum, we were able to actually make a calibration curve. So unknown concentration can be measured from this calibration curve. That was the whole point. So basically, we didn't do the DCDX experiment here. All we did is DCDT and measured allowed the permeation, allowed the kinetics to saturate. And then at saturation, these points are taken. Of course, only 4 points. As you can imagine, more is better, but at least it shows us the trend, and we can actually find a way to model even from these 4 points. So this is another useful experiment from the same instrument.
One quick question here.
Yes.
Just so I understand. The concentrations of this glycolic acid is in 4 different. One is first one is DI water. So we can
first one is right.
The other one is PPT, PPB, then PPM, right?
Oh, so 35 parts per
million, billion, trillion.
All right.
So it's
So
an
yeah,
exponential
million,
graph.
billion, and trillion, exactly.
So if you look at the concentration x-axis on the right side plot, these are
This one,
reflecting. Yeah.
yeah, right.
So also,
This is the concentration. So these are the known concentration. Those
right. Okay. I'm just trying to understand the relationship between the reflected intensity and the logarithmic scale of concentration.
right. So that comes from this model fitting. So
Mhm.
what happens is we have a way of modeling it's called empirical modeling, right? So this is the empirical model that was generated by the by the we have option of fitting just about any equation you can imagine, and maybe we should provide that as well at some point of time. So there is way to fit. If we have experimental data, what explains that experimental data, regardless of the physical
Right.
parameters? And this is basically a pure mathematical fitting of
Sure,
this
sure.
data. And that is the reason it says the x-axis here is ln x, and that's why it is ln, logarithm, natural logarithm of the concentration.
I was getting to is if we can fit it into log fit.
Yeah, we could probably do that too, right? And in that case, this equation would have been different. Then in that case, if I take logarithm on the y-axis as well, then you have problem on that model. So this is basically a model.
Sure. If it is from the log, if it is a linear relationship, that can probably give you more information for the relationship between the concentration and the counts, reflected counts. I'm not sure. I'm thinking loud.
It's possible to do that. This, the whole point here is to demonstrate that this kind of measurement, an empirical model can be worked out, from which we can calculate the concentration of unknown solution, whose concentrations are not already known.
Now, this is good by itself. I'm just thinking little next level.
Yeah, absolutely. That's a good point. And more can be done. And unfortunately, the most unfortunate part is that academia should be adaptable to this kind of ideas. They are not. Unfortunately, that's the case, because what happens is this transdermal drug delivery, right? How do they do that today? There is a thing called France cell. We have also France cell experiment done, but the France cell is there is a top chamber, there's a bottom reservoir, and in the middle they put that stratum corneum or some other substrate. And then if solution is applied on top, then that permeates through and goes into the reservoir. Then they draw liquid from the reservoir and put it in the HPLC. So this experiment may take week, 2 week, month. And that's what is being done today. But this is in real time. So our biggest challenge is how do we, as a team, all of us together, this is so much advantage here, so much capable, and yet we're not making any headway. How do we do that? How do we break in? It's not obvious. So a lot of things can be done here for sure.
Thank you.
Absolutely. All right. So more on the skin samples. The dermal fibroblast is a kind of skin cell. This is also another collaboration with Professor Rafaelovich at Stony Brook. They provided us this sample. Again, we try to embark on as many collaborations as we can. So, you know, and a lot of times we are lucky because many collaborations have the ability to produce application that one cannot do in other way. So one of the strategy for Miles that when you communicate and if they ask you for proof of concept, you can provide that as well. That would be kind of a collaboration.
Okay.
Yeah. And that's how exactly we did it. We went, I went to door, asked, you know, this is what it is, specifically by conference. I went to conferences. This collaboration came from a conference as well. The previous one, this collaboration also came from a conference. And this is also from another conference because Rutgers has a Center for Dermal Research, CDR. That's Professor Mishne Kohn is the founder and director. And, you know, believe it or not, I was the opening speaker for their center. So that's how we got connected with them. It takes some legwork, but, you know, we end up getting some result that otherwise is not obvious. So anyway, so the point here is that this sunscreen lotion have titanium nanoparticles in that sunscreen lotion. And it's not for sure if it helps or hurts. They don't know for sure yet. Because if titanium nanoparticles penetrates through the skin, that's a bad thing. But if they only stop the sunlight and do not penetrate to the skin, that's what they want. And that's what they believe. But there's no specific way of figuring it out or measuring it. So, you know, we have this cultured fibroblast cells, which is they made the cells on a petri dish and they provided us with that sample on a petri dish. So idea is that if nanoparticles, when you know, in a sunscreen, if you rub it on your skin, is the titanium nanoparticles are getting into the cell. That is not what they want, right? They want it just cover it, but don't penetrate into the cell. So what we did is we made measurements. It's like this. This is the whole cell. This is the same thing for other samples, as I showed you, stratum corneum. That's also have a cell that goes in here. And this is the petri dish that has all those fibroblast cells they have grown in their laboratory. So first we measured a blank petri dish, and then we have the control specimen, which is standard fibroblast cells they got from NIH. And then they have grown, and we have then characterized the depth. When the nanoparticles are applied, nanoparticle solutions. Those experiments are done by them. So we didn't apply any nanoparticle ourselves, but they had this control with titanium 1.05. That's their sample name. I do not know exactly what it means, but this paper outlines everything. Excuse me. And then what we found is, oops, sorry. There are other portion of the same experiment that data are not here because, so the titanium nanoparticle has 3 different kind of, what is they called, polymorph, anatase, there are 3 of them, I forgot now. So we wanted to see if we can discern those nanoparticles having different kind of the same crystal structure, but the polymorphism. So I don't have that data. I should have had that hit here, but those are published. And what I'm letting you know here is that even though titanium dioxide has different allotropes, but in fact, the T-ray measurement can discern them. There are probably 2 or 3 we have. I'll have to dig out those data sometime.
One question.
Yes, please.
For this protection of, sun ray for your skin protection or whatever, they're using titanium metallic.
In some, titanium nanoparticles being, I don't know if the point of this research was to that. Find out that.
My question is, are they really use titanium nanoparticles or titanium dioxide particles?
Titanium dioxide.
Dioxide. Okay.
Yeah.
Thank you.
Sure.
I think commonly titanium and zinc are the material or the substance.
Sorry.
Sorry, Miles, say that again.
Commonly for sun on the dermis or epidermis is zinc and titanium, maybe dioxide. I know it's a zinc and titanium compound.
Oh yeah, right. Yeah. Some of them. The other thing is that the companies are pretty protective of their actual formulation. So in the research case, and this is also, as you can see, in a petri dish research, so it's not on actual human or actual live situation. So the information that was provided, probably then the actual formulation, they can adjust their actual formulation. That's about it. All right, and then I think I'll skip the molecular chirality. That's a topic in itself. Contamination is, I already have discussed that. The last topic is T-ray Rahman spectroscopy. So we'll come to that later, next time. I think we can close the chapter in the next. Yeah.
One question before the end. Fick's law displayed on a slide maybe 10 ago. I comprehend, dC by dx or dC by dt, maybe a second difference of the concentration per position. Why Fick's law? Was there a purpose for the diffusion constant, or was there a purpose for J?
Yeah, so the permeation happens or diffusion happens most of the times because of the concentration gradient. In other words, particles diffuse from higher concentration towards lower concentration. So that's where dCdx, concentration gradient, comes in. If there is no gradient, then particles would not diffuse. So that's the basic premise of Fick's law. But then the kinetics is important because the rate of permeation is also important. So Fick's managed to make these two to work relate in terms of a constant dCdt, and the point is the D becomes a material parameter. This D is diffusion constant or diffusion coefficient. It's different for different material. So in other words, it's a way to characterize a material by measuring their diffusion coefficient. Miles was going to say something. Sorry, I interrupted you. Go.
Yeah, I agree. And I know D has different units depending on certain situations. Any information in the slides about D or J, or in maybe the paper that was below?
Good question. Yeah, we have information for J, but again, you know, the measurement of D is very academic. That needs, you know, if you want to publish a paper, you need to put a number on D. But practical things is the permeation happening how fast? That is dCdx. I'm sorry, dCdt. And what is the distribution of the particles along the substrate? That's dCdx. So these are the quantities that's more important for if you can measure them directly for a given substrate solution combination, then you know we probably don't even need to worry that much about the diffusion coefficient itself. But that said, diffusion coefficient can be easily calculated. J is the concentration itself, right? How many molecules I'm putting in there. So think about this experiment. You are putting, if let's say you put 100 microliter of solution, you know the concentration. Therefore, you know from Avogadro's law, you know how many atoms are applied here. So that's the J. That's the J per unit flux per unit area. That's J. And we're measuring this dx. So D is readily calculated, which we have not done. But again, from the experimental point of view, that's pure academic exercise. That measurement of calculation of D, because when you know J, when you know dx, you know, D becomes an ornamental quantity. But you can always measure it. In other words, if you want to write a paper on this thing, you obviously will have to put together those things and put a number for D as well. But good point. And a lot of exercise, you see, the measurements are not just for measurements, right? They're for measurements, but they also have other implication. So particularly in personal care industry, they need to characterize if you make a formulation, a solution, or in a lotion or something, they need to quantify if this thing is getting through the structure of the skin, or if it is transdermal drug delivery, then it must go to the bloodstream. If it is only a lotion, it must not go to the bloodstream. So, you know, all of those characterizations, there's no obvious way. But this gives a direct way of measuring those quantities and characterizing those quantities. If I see my thickness, let's go to the thickness profile. If I see that this thing is going through the 30, so stratum corneum is about 30 micron or so thick. So if it is going through that 30 micron thickness, that means it is eventually going to the bloodstream. And you can then make a, you know, take a whole skin, and we have also done whole skin measurement for something else in collaboration with another entity. There's also, you know, there's a compound called Seraphyll, and that Seraphyll is the one that helps moisturizing the skin. So then it becomes quantification of, if you apply Seraphyll to skin, how's that, you know, interacting with the skin, going through or not. So all of those, this instrument has the advantage in a very simple measurement technique, but a lot of implication. So we have this instrument in our lab. We haven't sold any of them yet, but we would like to eventually. We are, mostly our imaging instrument and our spectroscopy instrument are more, has more appeal at this point compared to this one. Any other point? Please go ahead.
I have a question. Sorry,
Yeah,
I was muted. The question is, in the two example you gave, one was hydrocortisone, another one was caffeine.
Mhm.
You used certain concentration for both cases.
Mhm.
But if you vary the concentration, increase or decrease, do you see the response in your?
Yeah, obviously. I mean, we have one example of not caffeine or or polyethylene PEG. But we have this glycolic acid example. If you vary the concentration, kinetics vary, as well as the gradient will also vary, which we have not measured yet.
Okay. Sure. Thank you.
Absolutely. So for today, then, I mean, I hope that next session will be the last session. All our material have been adjusted, and then the next session from the next one would be your presentation. How's that?
Who is going first?
I mean, if we don't want to lengthen too much, we can if 20-minute presentation, then 3 of you can have in one day, or at least perhaps Miles and Farin can do one day, and Dr. Majumdar can do the next one. How's that?
Okay.
So this Friday, each of us present.
No, this Friday I will finish.
Okay.
Then next Friday. So, so your presentation will be next Friday. Next Friday I will conclude the session, the workshop, and then after that, your presentation.
So basically you're finishing on 15th next Friday.
Yeah.
And after that following Friday is 22nd, Miles and Farin can present.
Right.
And I will finish up the presentation part on the 29th.
Exactly.
Okay, thank you.
All right then. So if there is no other point, then we can probably close for today.
Sure. Thank you.
Okay.
Thank you.
Good night.
All right. See you next Friday, everybody.
Yep.
Thank
Good
you.
night.
Bye-bye.
Bye.
That's